Hello and welcome to Embedded. I'm Elecia White. I am here with Christopher White. This time it's just going to be us. We're going to talk about more firmware security, but in a sort of different way. Before we get to that, because of our show with Jacob Martinez about Digital Nest, the place that gives access to technology to young adults, we are so fortunate that a generous embedded listener has decided to do a matching grant. That means that if you donate $1 to Digital Nest, they get $2, which is pretty cool. So I'd like to ask you to consider donating to Digital Nest. The website is give.digitalnest.org/embeddedfm. And of course, that will be in the show notes. If you have any questions, feel free to email me. And I am really excited that embedded listeners are going to help other people. It's just neat. Now let's get back to the show.
It's December and I don't care for it.
It's been raining and he doesn't care for that either.
These things may be linked.
We should just move to Australia.
Then it would be July that I'd be unhappy with.
That's true. Well, given that we are unlikely to be snowbirds, anti-snowbirds, I think we should just do a show.
Okay. You told me not to look at the notes, so I have no idea what we're talking about.
I was talking to Chris Wellens over at Interworking Labs, who are our corporate patron right now. We were talking about Rick Arthur's show, and she asked about the details of how security risks get exploited. We often talk about how important security is, and there are these top 10 vulnerabilities and all of that. But how do you go from buffer overflows and exposed pins to systems that are hacked?
How do you bypass the license check in VxWorks so you can install their tools when your company needs them and their licensing is broken?
Anyway, I thought we would. It really is. But I thought we would put on our gray and black hats and think about security. We are not experts in this, so my goal here is to think about it as you would. You know, if we have a design, why are you even worried about buffer overflows?
As a working firmware engineer, how do you protect against these things, or how do they work so that you can protect against them?
How do they work?
Okay.
I mean, it's fine. Like buffer overflow, I looked at it before the show because I know that a buffer overflow can lead to a security problem, but I hadn't really thought about how. And so we're going to talk a little bit about that. But it's all the things, the physical security, and just how do you go beyond security is hard to, well, here's what we mean.
Okay, so where do we start?
I think we should start as though we were...
Full disclosure, I'm not a security expert. I actually haven't really done much with this except, well, I guess I did some authentication stuff, but that was sort of a different area. So I'm at least going to be bloviating.
Bloviating, that means to just talk without reference to actual facts.
I'm going to be speculating to the best of my ability.
Thank you. Yeah. I mean, if we were having a meeting where we were designing a product, we need to use our heads. And I'm sure somebody out there will tell us, well, you forgot X, Y, and Z. And maybe we'll talk about those later.
That's fine. Or this is wrong. Whatever. Tell us if we're wrong. We're okay with that.
Okay. So let's start with if you had a device. Let's say they made a Baby Yoda and we were going to take it apart.
What? Okay. Well, how is Baby Yoda a device?
A Baby Yoda robot.
Okay.
Okay. And we were going to take it apart, of course, without hurting the puppet part, because how could you? And look at how it was made. What would be your first steps?
I mean, that's not a great example because I don't try to exploit a Baby Yoda robot. That's reverse engineering. There's nothing I can do with a Baby Yoda robot to cause harm.
Okay. I mean, this is part of it, is thinking about threat modeling. Okay, so I guess we could just go for the polygon.
Some sort of, I mean, to be interesting, it has to be something connected to me.
Okay.
Don't you think?
Sure, let's...
I mean, because if you don't, then your only vectors are physical, and the only harms are limited to its area of influence.
I say polygon because so often when there's an interview and somebody says, how would you design this? They point to the phone because it's the only thing in the room.
Okay.
But it's a reasonable thing. So if we wanted to hack into a voice over IP speaker phone in order to eavesdrop on super company secrets. Okay. Now how would you do it?
Okay. Well, first, I'd want to have one.
Yes.
And there's two important things I would want to understand, one of which is slightly easier than the other. But I would want to understand how it communicates over the network. So I want a good understanding of its network protocol, how calls are set up, how data is transferred, what those packets look like. So I'd want to observe that with some calls, maybe using Wireshark and other TCP dump and things like that to get a sense of that.
So eavesdrop on it.
Yeah, eavesdrop on it. And that's easy, and it has to expose that. You can't hide those kinds of messages.
Well, I mean, you can use TLS to secure.
Yeah. Well.
But this is the path. This is not the end.
Let's not solve their security hole before.
Yes.
Let's assume for a moment that not all the traffic is encrypted from phone to phone.
And whether it is or not, this is the first thing you look at. You look for the open doors before trying out the locks. Right.
And then the harder bit would be, for most things, I think, like buffer overflow attacks, the sort of thing where the first thing you're going to attempt. So to back up a little bit, the first thing that I would attempt would be to present messages to it that it handles in a buggy way. So sending it packets or packets with data in it that I can exploit some sort of buffer overflow problem. But I think in order to make that work, you kind of need to understand the firmware too. Right?
I mean, that is definitely an easier path than just trying all of the possible packets you can send.
And you need to know the architecture, right? Because if you're going to do a buffer overflow attack, presumably you want to run your own code on it. So you at least need to know what the architecture is and be able to write code for that.
And so that's actually where I would start, is with the question of how would you design it? If I want to reverse engineer something, I start with, okay, what am I looking for? If I have, whether it's a Baby Yoda robot or a Polygon, it's how would I do it? And then you open it up and you look for the things that you expect, and then look for the things that you didn't expect, and try to figure out what their purpose is.
Like what sort of things?
Well, let's say with a Polygon that is on a secure network, I would expect it to have some sort of EEPROM or flash that is probably SPI attached. I would expect it to have some sort of buffering system. And if it has an LCD, I would expect some sort of display buffer, probably external to the chip and SRAM.
Okay.
I mean, things I would look for. Because it's Ethernet, assumably, I would expect it to maybe have an operating system. Maybe not. These are pretty cheap, so maybe not.
It definitely has an operating system.
But that would give me the class of processor, which would then let me look around the board for what I think the processor might be. And so I would then take pictures of all the chips and try to figure out what all the chips do. Is this one just an audio decoder, or is this actually something else?
See, that seems too hardware focused.
That is my approach.
Yeah,
it may not be the right one.
Is that your approach to attack something? And not that you've ever done it, but
Yeah,
would
exactly.
that,
That would be my approach because, as you said, you want to get to the firmware, and the easiest way to get control of the firmware is to do something like a buffer overflow attack, which I promise we will define soon. But to do that, you have to understand what the chip is, and you need to have some expectations of what it's doing.
yeah, but some of that seems like periphery stuff to me. Like you can get bogged down in codecs and stuff. It's not really applicable to the problem. I mean, it seems like you'd want to focus on where the firmware is stored, how it gets conveyed to the processor.
But if I figured out that it was running VxWorks,
sure,
that gives me a different surface to look at.
Sure.
And if I figure out it is using this form of libc or that form of libc, that gives me a different way to peek in. Maybe I can now look at the code a little closer. So
it's a reverse engineering problem to start with.
Yeah.
Without even trying to attack anything.
For me, it is. And then I would also look at, the things I would use in manufacturing. I love command line prompts over serial. It's just, I do. And so I would look for one. And most of those are pretty easy to debug. If you can figure out the baud rate, that's the hardest part. So, yeah.
But that's assuming, that's kind of the exploration stage. Presumably you're headed toward, I want a remote exploit, because it's not, it's less interesting to be able to attack things that you have right in front of you.
Oh, absolutely.
Because, if you want to break something, a hammer is much easier than...
The goal is definitely a remote attack. But if I find out that they do, in fact, have a spy flash and they keep their own certificates on it,
right,
I'm almost there. I'm almost done.
You're almost done to do what? The certificates are going to protect, I guess, their communication path.
This is all, how is it designed?
Yeah.
Does it protect the communication path to their server, and their server uses the same certificates for every polycon out there? That don't do that. Then yeah, that's bad. Okay, so I've been promising buffer overflow.
It's only been 5 minutes.
I know,
promising anything
the whole time. So let's talk about that.
Because this is one of the primary ways to get arbitrary code running on something.
And it worked a little different than I expected. I'm going to put the post that I liked in the show notes. So if we don't make sense, feel free to go there and look at it. But the idea is you have a buffer of some fixed length, and it's maybe in the stack. So main calls this other function, which reads something from the command line and puts it in this buffer.
Or from the network, or from any external source.
Any external source. If you use some sort of string handling that doesn't take into account the length of your buffer, you can copy too much information into your buffer. Say your buffer is 100 characters. Normally, somebody types in, you have a hello world and you want it to type in their name. So they type in their name and it says, hello, Christopher, and then it exits. But that Christopher part was in a buffer that was 100 characters long. Nobody's name is over 100 characters. Why would we bother? And if you haven't felt that logic at some point, I don't know, so many times. Command's never going to be longer than 35 characters. This number's never going to need more than 12 digits. Anyway, there's a fixed buffer size, which is, 4 times more than you thought you needed. So why would it break? And then you copy in from some other source, from the internet, from the command line, from your user, however. And you just copy into this buffer. It sits on the stack, and as you overflow the buffer, as you go from...
Which it allows you to do because this is a bug that somebody's written. They're not checking the input length.
They're using strcat instead of strncat. They're using...
strcopy instead of strncopy.
Yes.
Okay.
And so when you called this function that said, get and print out their name, you put something on the stack called your return pointer, and it tells you where to go after you're done. It tells you where to return to. And as you overflow your buffer, you get access to that pointer. You can overwrite it. And if you think about that, as soon as you get to the point where you can make it jump to any address, you can make it run your code. Because instead of putting in 100 bytes of my name, I wrote this tiny little program that loaded other programs at the command line. Hypothetically.
Okay, that's going a little bit too far, I think, at this point. Let's just say it does something simpler. But loading other programs requires...
Okay. I wrote this tiny little program to instead print out the
password database.
The password database.
Sure.
To print out some piece of memory.
Something you want hidden.
And so I now take this function pointer that it's supposed to, this return pointer, and I point it to the beginning of my buffer. And now it executes my buffer. And, string copy doesn't care what's in the buffer unless you have a null terminator.
So let's back up a little bit. Because
Okay.
we talked about stack and we didn't say anything about how that works.
Okay.
So the stack is a kind of memory in your program. And pretty much every system, operating system or not, your code has what's called a stack as a section of memory.
It's usually invisible to you.
Yeah. And all of anything within a function that's a variable gets put onto the stack. And the stack, it's called a stack for a reason. You put stuff on it and it grows in one direction as you stack things onto it. And stacks grow, I'm going to get this wrong, downward in memory. So if your stack starts at address 1000 and you push 100 hex bytes on it, now the stack pointer moves down to 900. Right? Okay. So as you put more things onto the stack, it grows downward. But when you copy buffers, they go the other direction because addresses increment. So you put items on the stack in a downward fashion until it runs out. But items themselves get written in increasing address order, as you might expect.
Arrays get written in increasing address order.
The stack is also used to store state between when you call functions. So it's not just here's your variables, it's also here's the registers that as they were before. Here's some set of registers as they were before I called this function, so I can get them back when I return to the function. One of those registers says, here's the function to go back to when you're done. So if I'm in main and I call printf, before I call printf, the C runtime says, oh, you're about to call printf. Let me gather some stuff up so that, what?
I mean, the compiler does some of that too.
The compiler.
You said runtime.
Or whatever. Yeah.
It's not Java.
What? There's a runtime?
Yeah, but all right.
It's not a virtual machine. It's
Yeah.
the infrastructure to make things work. Anyway, it pushes that state onto the stack, and one of those things is the return pointer. I already said that. But now I'm kerfluffled because I don't know where I was.
Puts the variables on, it puts the return pointer on.
Right, so you're calling printf. So right before you call printf, it pushes that stuff on the stack. One of the things is, how do I get back to main? Okay, so printf finishes, and when you call return, at return, that's when all that stuff gets popped back off the stack, and it repopulates those registers where it was supposed to go, including the return address, and then it calls the return address.
Jumps to the
return address. So what you're describing is you have the stack, you get this name variable, which gets pushed onto the stack, which is 100 bytes long. Somebody writes 200 bytes to it, and it goes off the top of the stack, including to the place where the return address was written. So there's a kind of a chicken and egg problem there that I haven't quite worked out, but
the
return address has to be written first. So
yeah, the return address happens.
Okay, right, and then you call printf or stir copy and then it overwrites. Yeah, so that works.
And one of the tricks here is you have to figure out how long that buffer is.
Yeah. Well,
but that's
doesn't
actually
have to be perfect, right?
No, because if you just write some bogus thing in there, you'll get seg faults. As soon as you've overflowed the buffer, you'll get a seg fault or a crash.
Right.
And then
depending on how good your system is, a real embedded system will probably just trundle along happily.
Not if you trash its return pointer.
If you trash it with something valid.
Happily trundle along randomly.
I said valid.
Okay.
So somewhere within the buffer.
Okay.
But it's not going to seg fault.
You might get the interrupt that you tried to run from memory that is invalid.
Right.
Or tried to execute an invalid instruction.
Maybe you caught that, maybe you didn't. But stuff like writing to writing to 0, for example, that's often not caught unless you've done special things or have special hardware that can catch that. Like, I think you need like the MPU on the Cortex M4 to map out the 0 page. But we're getting off.
Yeah, I'm not sure you do, but that's a separate discussion. Okay, so now we've sort of discussed the overflow. And the reason people use this is because it's pretty easy to use. You just send it a bunch of buffers. You just send it a bunch of characters. And if it fails, then okay, now I have to figure out where it fails. And once I know where it fails, I can figure out how to adjust the pointer the way I want it to. I can send it code that I want to execute, and then I can execute that code. Okay, so that is bad, right? I mean, as soon as somebody can execute code on your system, that's bad. And whether it's command line or in our Polycon, if we could do that over a generic internet.
Yeah, well, that requires several other steps, but yes, bad.
I mean, that's the golden ticket here. Right. Then you can eavesdrop on anybody's Polycon. If you can just send something to a phone and say, okay, I'm going to execute code. Now I also want you to make me a party to this conversation.
Right.
So, yeah. Okay, so that's buffer overflow. That's one of the big ones, and it's probably the one that we talk about the most.
One, right? I mean, and it gets more complicated because, well, we said, the chief reasons why this is exploitable is people forget to use like sterncat and things with an n. The n in there says number of items, and it doesn't copy any further than n. If you use the ones without n, it can copy indefinitely, and then thus be your buffer overflow. As people got wise to that and started doing the right things, the ways to find buffer overflows got more and more complicated. And so now there's like, I don't have a good example, but it's like cascading levels of bugs. Like, okay, I sent this packet, which put this in this state, which means it was ready to accept blah. And, or there's a bug in the JavaScript JIT compiler, all sorts of very much more subtle things than merely, oh, this person forgot to copy a string properly. So these buffer overflow exploits still exist even when people are being conscientious, is what I'm trying to say.
But mostly it's because of multiple failures. And if we could get our systems to require multiple failures, then...
And they get harder and harder to find because of that.
Yeah. Multiple failures just means it's more expensive for someone to hack your device than it is for them to build their own. And that's part of threat modeling, is figuring out where your okay point is.
Yeah.
There's the whole, I don't look good in orange. I don't want to see my face on the cover of Wired.
I don't want to get sued for billions of dollars.
Yeah, there's different layers, and this product can kill somebody, so we have to be very careful. Or this is a children's toy, and the worst thing that can happen is someone makes it say foul words, which then goes up on the internet, and we're embarrassed. Okay, that's embarrassing, but really they could have just faked that video. Whatever. Okay, so that actually is number 1 on the OWASP Embedded Application Security Top 10 Best Practices list. OWASP is, we talked about that with Rick. They look for making, for security and best practices. They actually have a lot of information.
What does it stand for?
I don't know. It's like a O and a WASP. Open Web Application Security Project.
Thank you.
You could have looked that up yourself. Anyway, the first thing on the embedded application security list is buffer and stack overflow protection. And it's using things like sprintf, scanf, strcpy, and strcat. The ability to corrupt memory and make it do what you want is bad. And we talked about the stack. That is one way to do it. You can do things from the heap.
Yeah. Other memories.
You can do things from global memory. If you made your, I'm not gonna put the 100-byte buffer on the stack. That's ridiculous. Who would do that? I'm going to put a static here, so it goes into the global BSS memory. Yeah, you can still do stuff.
The neat thing about these exploits is they're also the same class of things that are some of the hardest bugs to find.
Exactly.
Stack overflows, memory overwrites. I mean, these are all things that people who've been working on this kind of software engineering for a long time have seen over and over, and they're very hard to find sometimes, even when, it's your program itself that's causing the corruption, not some outside actor. So it can be very hard to defend against something that you can't even really detect at runtime.
Oh, yeah.
Easily. Even if you've got a complete dump, it can be a core dump, or you're watching it in the debugger. It can be sometimes maddening what's happening, because once this stuff starts happening, all the state gets corrupted everywhere.
Well, and if you were modifying your buffer, but your buffer didn't modify every point, you might still get a good return address. But now its variables are messed up because its variables were put on the stack. It just is, stack corruption is bad.
You were mentioning the globals too. That's a great exploit, because you don't know where the compiler and the linker are going to necessarily put things. You may see stuff in the file listed a certain way, but it's free to rearrange things. So when you look in the map file, and I've had to do this with memory corruption bugs in the past, it's like, all right, I'm doing graphics. What is this data that's coming in here?
Who's overwriting my data buffer?
I know the name of my variable that's getting creamed, right? So what's how do I find out what that data is? Because it just looks like data. Well, you look at the map file and it says, oh, this one, the heart rate
buffer is right before this.
The buffer is right before the graphics, this graphics linked list that I have. Yeah. And that's causing a crash. Now, why is the heart rate buffer? And it's overrunning its thing, and it's something from another component of your embedded system entirely that somebody else works on. Not even in your files, not even in your directory, in a different module, but the map just, the linker decided, let's put this next to this. It fits nice. And so stuff, those kinds of corruptions can come from anywhere. So with these exploits, it's like, you may have done a good job, but did the guy down the hall do a good job with their component, which happens to be contiguous in memory with your data? So it may not be your fault at all, but you're the one running the arbitrary code out of your buffer.
When I was talking to Chris Wellens about this, I didn't do a great job at the beginning talking with her, because I was just like, well, it's kind of the same as debugging, but in a system you don't really know. Yeah.
Well, it's reverse engineering, right?
Yeah. But so many of these things I've never used a buffer overflow for debugging something.
Right.
But I have had to identify buffer overflows. So it is something I'm used to from an engineering perspective. The second one on the list is injection prevention, which is best represented by Little Bobby Tables and XKCD comics, where somebody intentionally does something bad.
Exposed a command to the outside world that you didn't intend to. And so you get a command into your command processor through weird means. So like in the Bobby Tables example, somehow somebody's typing SQL into a field that just happens to get executed because you didn't detect that was just regular text, not SQL you should execute.
I saw a good example of this where they were executing a command. So it was kind of sort of like our Hello World example, broken down as instead of hello Christopher, you would instead have a command you wanted to run, maybe always output data to a file, or like less or more. You pipe to those, but you would, instead of file pipe more, you would instead say my reader file, and it would do the same thing, format it for you. But if you have it run commands so that you can, look at the results of commands in the same format, it will run any command. And as an engineer, I might be like, oh, okay, so my reader will run PS or some function. And because I'm like, okay, it'll run PS-EF. I don't care. It'll do the parameters. But I'm only going to let them run one command because, that's safe. Yeah, but then somebody will put a semicolon in it, and then they'll run an entirely different command as you, because that's what you've set it up to do. It's about looking at what people send you and actually looking for attacks. Unlike buffer overflow, which is something that happens to the best of us, injections usually are intended to be malicious. That isn't to say that I haven't shot myself in the foot by failing to look at whether or not I'm getting floats or hex or integers. That's another way of looking at sanitizing your data. So that's a pretty good one, because you can, like little Bobby tables, if you haven't seen the XKCD, the thing is somebody names their child like Robert drop table all users : whatever, SQL query, SQL command in the middle of the child's name. And then the child goes to school, and the school cannot function because they put that in their database, and it's Bobby and then a command, and executed it, and then deleted all the users. Yes. And so we call him Little Bobby Tables. And it isn't even always on purpose. Why can't names have semicolons in them?
Right.
Just because that would break so many things.
Yeah, and that's all about sanitizing your inputs, which, with the Polycom example would be the network attack, right? It could be a buffer overflow, but it could also be by looking at their protocol and sending various malformed commands, can you disrupt the system? And sometimes it's not just, I want to hack into this and run arbitrary code. Sometimes it's a denial of service attack, right? If you find something that crashes it. If you, for example, wrote an implementation of OSPF for a core router company, and you just happen to discover that if you accidentally miswrote one of the packet formats, and you always crash the Juniper routers.
Really, whose fault is that?
It's Juniper's fault. It was Juniper's fault. I mean, they should sanitize their inputs.
Yeah.
Yeah. But I mean, that's a big deal, right? I mean, that's if you find a packet that can crash a router, it's pretty easy to get a packet to a router, right? So you can do all kinds of damage with that, take down systems. And then, if you just keep sending them, what's their recourse? They're not going to get a firmware update real quick. So that kind of thing can be very insidious.
But this is about, when I think about engineering and debugging, your coworkers can definitely do this to you by accident, by sending you data that you don't expect. And so it's about designing APIs that make sense, and then checking to make sure untrusted users are using your API correctly.
Well, or making sure your API can't be used in a malicious way, which is harder, but...
It can be, because I don't really want to check to make sure that all Boolean variables input are either 0 or 1.
It depends on what your device is.
It depends on what your device is and who's calling your functions.
That goes back to threat modeling, right? If you're making a seismometer that you can access remotely, probably not a big target, right? So you can be a little more relaxed on these things. But if you're making an internet connected toaster oven,
and you don't want to light somebody's house on fire,
and they can be turned to a thermal botnet. You should be paying more attention, or industrial controls, or things that government actors like to hack into. So that was injections.
Injection prevention is the thing you should be looking for. The next one is firmware updates and cryptographic signatures.
Yes, this is the 2-meter exhaust port of your.
Yes.
of your device. I mean, there's not.
I can totally hit womp rats.
Actually, this isn't the 2-meter exhaust port. That's hard mode. This is like I don't know. I don't have a good analogy. It's the open front door that you can't adequately lock. So yeah, this is. I mean, if you have user upgradable firmware or remotely upgradable firmware, this is really hard.
It really is,
because you're delivering the code, right? If you want to run arbitrary code, the easiest way in is on the truck that delivers the code.
Yes. How did you break into the bank? Well, you see, I dressed as money.
I got a job as a vice president, opened the vault, and took all the money.
Yes.
Sometimes that's easier.
Yeah. Okay, so firmware updates.
I don't know how much we can talk about that. That's a whole 4-show.
I think the thing that I want to mention here is, again, back to, this is something I have dealt with as an engineer. Firmware updates, I put them together and I send them out. But I have had to hex edit firmware updates. I have had to decompile parts of them in order to look for things to see if that bug was fixed, even though it was supposed to have been fixed in this release and nobody's quite sure which got compiled. I have had to look at the crypto on it to make sure it was applied correctly, to try to open it with the wrong crypto just to make sure. I've had to, I always have to open it with the right crypto to make sure. There are so many things we do in debugging that, you have to think about this. And doing it wrong in debugging often leads to it being an attack point in production.
Yeah, and the firmware thing, it's a different class of problem because it's not like I'm writing normal code. Let's say I'm the GUI person. My job is to write GUI code. It's not foremost in my mind that I should be thinking about security. Like, okay, if somebody interacts with the input panel in the right way, they can do a buffer overflow and gain control of the system. It's not top of mind.
Can you imagine on a refrigerator typing in your opcodes?
But it's not top of mind. You're working on the feature you're working on. Whereas with firmware update, that's kind of like, this is the main vector through which somebody could take over my system, and that needs to be like job number one.
And it's not just...
It's a security job, not really a firmware update job.
It's not just they can replace your code with their own, which is, that can be bad, but they might as well have rewritten the system. They can... The hard thing is that the thing that a black hat would want to do is to take your code and decompile it so that they can read it more easily. And that also often means...
They find your buffer overflows or whatever.
They find your buffer overflows. But also, they can look at libraries. And so you don't just get all opcodes and horribly written C in a decompiler. You also get function calls.
Yeah.
Oh, look, here's a string copy. Oh, look, here's a mem copy.
Yeah.
And the more libraries you use, the easier it is to see.
So that's getting the firmware and then finding attack points rather than replacing the firmware.
But then you replace the firmware with what you have, and since it's so close to what they had, it does exactly what you want, and they can't tell the difference.
Extra.
Plus a little extra. Yeah. I totally agree. Firmware updates it's just so hard. And if you can buy a solution, you should be thinking about that. It's something that is just getting harder all the time.
Yeah.
So next on my list is securing sensitive information. Do not hard code secrets such as passwords, usernames, tokens, private keys, or similar variants into firmware release images. Have you ever done that?
No.
Really?
I don't believe so. Hard coded a key into no.
Oh no, not into a production release. No, the manufacturing software I've hard coded passwords and felt very bad about that. Felt very guilty. But the problem here is that. So how are you going to secure sensitive information? You can send it out to a spy flash? Are you going to send it to a file system?
So usually there's another device.
You can send it to an expensive little part that all it does is this?
That, or your SoC has what's called a secure enclave on it, which are, sequestered little memory spaces where you put these kinds of things that can't be read out except in certain ways, or can't be read out at all. They're write only, and when you're doing a authentication challenge, you say, okay, here's my thing, and it returns you the result of the cryptographic operation. Stuff like that. I've done authentication systems for consumables, and we had a little extra device, and that had the key in it. It was not readable, theoretically. And there was another one in the consumable, and they had a little transaction. And those chips both had the keys in them, sufficient keys to do the cryptographic authentication operation, but they were not in our software anywhere. And so those had to get written at a certain place. They had to exist in some software on some database, but it was in a computer on premises in a cage with access controls. And we still got hacked. At that job, did everything right until somebody figured something out. Never quite sure what they figured out, but we kept adding on layers of things to try to prevent it. I think what probably happened is that somehow the key got out. Either at one point we got a shipment of the chips from the company and they were defective, and you could do a lot of things with the cryptographic chip you weren't supposed to be able to do past the blown fuses. So that was a little odd. So something like that happened. And then once the key gets out, it's very challenging because you might have thousands of units in the field or thousands and thousands of consumable devices with the old key in them on shelves, and you can't revoke it. You can't change it. So that can be a real challenge. But that kind of operation where you have keys stored, it's not just for external devices, it's for firmware updates, right? For communicating with your cloud service and saying, oh, this is a legitimate device. So protecting those is rather difficult. And that's more of a challenge because I'm not sure you can really hide some things. Like for some things, there has to be a key in Flash, right? And you can make it easy to change if something goes wrong, but
I mean, making per device keys so that you can't. Yeah. So that when you hack one device, you don't get control over all of them. But then that means you have to have a database of all devices and what their current keys are.
And it doesn't work for certain situations. Yeah. Like the consumable one, you can't do that. You can't ship a different version of the consumable for every device. Every
master device. Yeah. I mean, the only advice OWASP suggests is, if at all possible, sensitive data in clear text should be ephemeral by nature and reside in volatile memory. And by that, they do not mean the global memory, because that's not really, I mean, it is volatile, but it's not, and they don't mean the keyword.
RAM.
Anyway. RAM that is reused often, not just RAM.
Yeah, and people make mistakes with that too and forget to, I think there was with like one of the password managers, which is a difficult job.
Yeah. It's got a big target on it too.
They had the master password stored in RAM, and they had intended, I think, to clear it right after use, but it just hung around. It's hard to know what computers do because they stick things in caches. They, stuff migrates. But that's all. I mean, that's different than embedded because, it applies, but those are, when you're dealing with Linux and full operating systems, there's all kinds of other considerations.
Let's see. The next one I have is identity management. User accounts should not be static. You should be able to change your passwords and internal web. I'm not even going to worry about that one.
It's for IT people.
The next one is embedded frameworks and C-based hardening. Things like tool chains and libraries, frameworks, other people's code, embedded Linux systems with BusyBox and Yocto and Buildroot.
And things with executables that are so out of date, they've got 100 cert advisories against them, but it's hard to update the Linux that you shipped.
Or that one version of PSOS IP, TCP IP that existed for so long, had so many bugs, but it was in, thousands of different products because it was super cheap and everybody used it.
Yeah.
I'm sure there are libraries now that are being passed around that, oh yeah, I'm going to use that because I used it in my last project and it made sense. And so the more monoculture we get, the easier it is to attack because you can just focus on the attack on one spot.
And embedded, so many of those libraries are just kind of small company produced things that don't have a lot of people working on them. They're not probably thinking about security. Some of them started in the late 90s or mid 90s or the 80s even, and are these old legacy code bases that just hang around because, hey, it's embedded.
We never change.
Use Bob's RTOS. It's great. And then somebody sticks a TCP IP stack on it from who knows where, and then, super easy to exploit if somebody bothers to spend the time.
And when we say exploit here, we're talking about all the things we've already said. We're looking for buffer overload runs. We're looking for dependency injection. We're looking for common points of failure. Okay, so use of debug code and interfaces. Well, yeah, it's always nice to remove all of the pre-production code before you go to market, but then how are you going to debug it in the field? Is that a backdoor? Yes, it is. All those things that make things easier to debug, they make things easier to manufacture, also make it easier to hack.
Right, because that's what you're doing, right? You're
by nature.
You're opening your device specifically so you can modify the deepest parts of it in an easy way. Okay, you've opened your device so you can modify the deepest parts of it in an easy way. So yeah, it's a balance there, and it's really hard. And you have manufacturing folks yelling at you because something's too hard to provision in the factory, right? And then somebody makes a decision somewhere to make it easier without consulting someone, and suddenly all bets are off.
I had a CM that once refused to blow the security fuses on a board. They're supposed to do it on every system.
And what do those do?
Those made it so you couldn't JTAG read out the code.
Gotcha.
And they were just like, no, because then
I wouldn't be able to read out the code.
No, they were like, oh no, because then it can't be updated, and when you send us new firmware, we won't be able to update it. And we're like,
that's the idea.
Yeah, that is the idea. We are aware of that. Please only do 10 at a time or something. It was just they flatly refused. They were like, we will not do this. And I imagine they've had bad experiences where they blew 3,000 fuses and their client said, oh, we need to update this firmware and it's your fault. You shouldn't have done that ahead of time. I understand why that happens, but if your chip comes with security mechanisms, you should use them and you should figure out how to make them usable in a fashion that makes sense financially for your product.
Yeah, and it goes back to the threat model, right? Who's going to attack this? Why? What are the repercussions? And
how much is it going to cost us?
And some of that doesn't occur until you've become a success.
Yeah.
It's like you might be thinking, oh, I'm going to sell 10 of these. It'll be fine. And it takes off and you sell 1,000 and maybe 20,000, maybe 100,000. And all of a sudden you get on somebody's radar as, oh, that's a big footprint. Let's see how this works.
And it can start with, let's see how this works, to, oh my God, this is so cool, to, oh, look, I can just shut everybody's off.
Yeah. Or I can mine a lot of Bitcoin with this.
So we're almost done with the top 10 for embedded applications. Transport security level, transport layer security, TLS.
Mostly for networks.
That's mostly for networks, but it's a thing to consider.
Yeah.
Every time you are putting things outside your system, whether it's a SPI bus or an Ethernet or Bluetooth, the security there has to be considered because it's a weak point. All of your doors and windows are weak points in your house. Okay? Yeah. Data collection, usage, storage, and with respect to privacy, yes. I don't think that really belongs in the security list.
It's.
I mean, it's important.
It is security, but that's database security.
And they're talking about leaked numbers and how that can be terrible. And I agree. I guess the point here is just to limit the amount of data you store.
Don't store your customer's bank account and credit card information on the thermostat. Or do,
whatever. And the last one is third-party code and components. We've already covered this. It was already in the list, too.
Yeah.
Man. Yeah. All right. Anyway. Yeah. Security is hard. And security is hard because there's so many ways to do it wrong. And because so many of the ways to do it wrong are the things that we do right as engineers.
What do you mean?
Like making things easy to manufacture.
Oh, I see what you're saying. Yeah. Being conscientious to your coworkers or to the rest of the company.
And the things we do to take shortcuts because
I was about to say shortcuts,
our time is so limited often.
Yeah. And there's all the intentional backdoors we put in.
Speak for yourself. But it's more, for me, it's sometimes the time. It's like, yes, you should absolutely do per key encryption per system. And you should keep track of it. And you should be able to turn off only one system. And you should be able, if one system gets hacked, to not affect any others. Yeah. The manufacturing database is just hideous sometimes it is totally worth doing that, but most of my clients are going to say, how about we just put in one key for the first 1,000? And how am I going to say no to that? They're trying to build 1,000 units. They've only got budget for 12. It's a balance. And that's why we do threat modeling. How often do you do threat modeling?
No.
Never.
I don't have clients that
need it.
I need it right now.
Yeah. I've done a couple.
And the last few jobs where that wasn't my part of the job.
But to me, what you just did is where I would start with threat modeling. You take the list, you go through, you talk about your product, you talk about who might attack it, you talk about what steps you need to do to prevent it. And
it's the same kind of thing you do with the hazard analysis for a safety critical device. So you list the things that could go wrong, you give them a severity, and you list mitigations, or you start to think about mitigations. And then you sort them by severity and whether
ease of fixing.
Whether the mitigation, usually you score the mitigation for like how easy it is, and then you subtract, and then you sort by what's left over, and do the most severe ones.
Do the easiest to fix and the most severe.
You got to be right. I mean, this is all
estimation.
Yeah. There's things you're going to miss. So
there's a whole nother top 10 list for Internet of Things, OWASP. It's basically the same stuff, but a different order. They do talk about default settings in devices and how you should probably not do that. I came across some cameras recently, some web cameras, and they were pretty expensive. And they were spec'd to make sure that they had no traffic to parts unknown. So they were really quite expensive. And they had the stupidest password and the stupidest username. And it was easy to change. And I went out and I looked online just to check. And there were, people had identified huge numbers of cameras you could get to with just the default root name and password.
Yeah, in some sense, it's good that those people are out there because those are the easy things to attack and people go for them. Ignoring you. But yeah, people, there's a stratum of the kinds of people who attack things, right? There's the sophisticated people who are going to go through all the effort of reverse engineering, trying to get the firmware out, reading it, understanding it, finding ways to attack, and then, producing a whole exploit and then using it. And then there's the people who are just kind of along for the ride, and they're, going to these websites and finding, oh, this is how you get into this product, and then going and doing it. And so there's fewer of the people who are spending the time to really understand and generate the exploits compared to the people who are just using the exploits that have been published somewhere.
Yeah, absolutely. Because it's easy to use the exploits.
And that's the problem, right? Once somebody, it only takes one person who's gone through the effort to produce maybe 100,000 people in dark apartments.
I wonder what this is kind of like how many golf balls are in the state of Kentucky. I wonder.
Trick question. Kentucky does not exist.
I wonder the population of experienced security researchers with a willingness to be black hat.
Yeah.
The population of, let's call them script kiddies, and the population of software engineers. How many people are we defending against? Is it 10? Is it 100,000? I don't know. I don't even know the scale.
It's probably hundreds of thousands of script kiddies are on that order. It's probably thousands or less of, I don't know.
And not everybody wants to do anything bad. This whole camera thing, you could pan and tilt so you could change the stuff, but most people just didn't really care. They were just doing it to look at parking lots and surf locations.
That can be bad.
It totally can be. It can be used nefariously.
I've seen Batman. Which one was it? The Dark Knight. We got all the cameras. That was very bad for the Joker.
Oh, were you on the Joker's side?
Violation of the Joker's rights.
It was certainly an invasion of privacy. And I don't think you can do what they do on the cop shows, but...
Enhance. You can now with neural networks. It'll just fill in something that looks right.
Something random. Yeah, watch which database you used for training on that one. All right. I will post the top 10 that we just went through.
I did want to point out, I forgot, there are tools that you can use to try to attack your stuff too, and I don't have any offhand. But things
OWASP
that will go through
here.
and attack your software, find all the inputs, send all kinds of random input, fuzz them. It's called fuzzing. There's ways to harden your stuff without just sitting and thinking. Kind of automated tests to find ways in. And to exercise your APIs and things. That can be quite useful.
Yeah, so they have a tab called...
Because that's what other people are using to find exploits too.
That's true.
So you might as well try it yourself.
Embedded device firmware analysis tools. And it goes through the hardware stuff, but there are also some software links. And it goes beyond GDB and IDA, which is one of the big decompilers, and lists things you can try. And if there's any chance your audience, I don't know if they're customers, is going to use these things, you should absolutely try them too. I'm sure that your boss will let you. And by the way, could you record that conversation? Because it's hilarious. They also have a book that describes a lot of this stuff and how to think about it and how to manage identity and whatnot. So there'll be lots of links. And all I can say is, no, you're not going to solve this today, but maybe it's one of those things that if you could just get a little better this week and a little better next week, then
or if you just
maybe
realize
in 25 years we'll have good security.
Or if you just realize how big a problem it is, and that maybe you like most of us, don't fully understand all this stuff, that's a step forward too.
Oh, yeah.
Danger, Will Robinson.
And being able to talk about it. It's not just security scary. It's, I can make the security better in these ways for this reason, in this amount of time, and we should do it because it will otherwise cost us that amount of money. And as a manager, that's a much easier choice. All right, so I guess that's it. Thank you to Christopher for blabbing with me, bloviating. Thank you for listening. Thank you to our patrons for supporting us. We don't know why you do, but we're really glad. I mean, it's really nice to have somebody say, yeah, what you do is interesting enough and important enough that I'm willing to kick in a few bucks a month to encourage you to continue doing it. So it's a weird sort of validation. Also, it pays for a lot of stuff, which is awesome. And finally, thank you to our corporate patron, IWL, Interworking Labs. So now we have Winnie the Pooh. Oh, right. He's stuck in the door to Rabbit's cave, and Rabbit is hanging his washing on his feet.
Christopher Robin. He's been stuck there for a year.
Christopher Robin's in the front. So he took hold of Pooh's front paws, and Rabbit took hold of Christopher Robin, and all Rabbit's friends and relations took hold of Rabbit. And they all pulled together. And for a long time, Pooh only said, ow, and oh. And then all of a sudden he said, pop, just as if a cork were coming out of a bottle. And Christopher Robin and Rabbit and all Rabbit's friends and relations went head over heels backwards, and on top of them came Winnie the Pooh. So with a nod of thanks to his friends, he went on with his walk in the forest, which started like a year ago, humming proudly to himself. But Christopher Robin looked after him lovingly and said, silly old bear. Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.